Electrolysis. We've been talking about voltaic cells that generate electric current. An electrolytic cell utilizes electrical current to drive a non-spontaneous reaction. So it's the opposite of a voltaic cell. The process is called electrolysis. So as an example, the fuel cell we just talked about, hydrogen and oxygen react to form water. That reaction is spontaneous. In a voltaic cell, in a fuel cell, it produces electrical current. But if we supply electrical current, we can cause the reverse reaction to occur. So we can take water, pass electric current through it, and break it into hydrogen and oxygen gases. So this has some potential here. We could use a solar-powered electrolytic cell to generate hydrogen to power the fuel cells. Right? So we're using energy from the sun to drive the reaction in reverse, and then we reserve those gases, and when we want to use them, we put them into the fuel cell, and we can get the electrical energy back when we want it. Right? So this all sounds great. Every transaction, though, you're losing some energy to the heat taps. Right? So, like I said, people are working on it. Here's an illustration of the electrolysis of water. Here we have water with some sort of a soluble salt in it, because pure water doesn't conduct electricity very well. So you're not going to get any electrical conduction in order to generate the oxygen and hydrogen. But if you put some sort of an electrolyte in there, then the current will flow, and you're going to get oxygen bubbles from the anode and hydrogen bubbles from the cathode. And these will generate a hydrogen and oxygen gas in stoichiometric amounts. You'll get twice as much hydrogen gas as you get oxygen in terms of numbers of moles. Other uses of electrolysis. We can use electrolysis to reduce naturally occurring metal oxides to produce the pure metal. You go out into, the great wide world and you're looking for metal. You need some iron. Where do you get iron? Well, you can mine gold and silver because they are very inert. They don't react much, right? But you're not going to find just pockets of iron because iron's very reactive and it forms rust, right? Most metals are found in compounds, oxides, or other compounds, and those are the ores that you dig out. So you find this particular substance that's rich in iron, then you need to get the iron out, and electrolysis is one way to do that. Sodium metal. Sodium is very reactive. It reacts with the moisture in the air, so it's not like you're going to find sodium metal just hanging out somewhere in the dirt. But you can produce sodium metal through the electrolysis of molten sodium chloride. Now you got to get it pretty hot, but you can melt sodium chloride and pass electric current through it. Wait, that's the wrong picture. Sorry, don't look at that picture yet. Pass electric current through it, and you can produce sodium metal at one electrode and chlorine gas at the other. Electrolysis is also useful for plating metals onto other metals. Now we look at the picture. This is an electrolytic cell for silver plating. So in the old days, it was common to have silverware. That's why we call it silverware, even though most of us are not using silverware. It's like stainless steel ware or something, right? Your spoons and forks and things. They were solid silver. Okay, well, that's really expensive stuff, but it's beautiful. And so to make things less expensive, they discovered that you could take a cheaper sort of metal and then just put a thin layer of silver on top of it. And it looks very much the same. And that's called silver plating. So you can take a less expensive metal and coat it with solid silver. So here we have a silver, it's probably a silver chloride solution. No, not silver chloride, that's insoluble. Something like silver nitrate, most likely. And you pass an electric current through it. Here is the object that you're wanting the silver to deposit on, and so you make this the cathode. And you're forcing electrons into that, and that attracts the silver ions, and they are reduced at the cathode. At the other side, you have a silver electrode, a silver anode, and you're taking electrons from this, that's producing silver ions, which then go over and get deposited on whatever object it is over there. This process of plating metals is used in many, many situations. It's one of the ways that they make electronic circuit boards, is you can actually electrodeposit the conductive metals onto those boards. Pardon me?
You can also de-rust things.
You can de-rust things, yes. But you don't quite get back the perfect, beautiful, original object.
A lot less scrubbing, too.
A lot less scrubbing, this is true. Or you can pour Coke on it. Coca-Cola takes off rust pretty well, too.
It's a lot of Coke.
It is a lot of, you just soak it in there. So here is a comparison between a voltaic cell and an electrolytic cell. The electrolytic cell, the current flows spontaneously. Here it's going, we have the oxidation of zinc and the reduction of copper. In the electrolytic cell, we are using an external power supply and forcing the electrons to move in the opposite direction. So now we're taking zinc ions and reducing them, and we're oxidizing the copper to Cu2+. The voltage that's required to do this is going to depend on the specific half reactions that are involved. These two half reactions in a voltaic cell will generate a current or a voltage of 1.10 volts. In order to drive this in the reverse direction, you're going to have to apply greater than that voltage to get it to go. Another thing to note in here is in the voltaic cell, the zinc electrode is the anode and the copper electrode is the cathode. In the electrolytic cell, it's the opposite because we're forcing the electrons to go in the other direction. And that's what's determining which is the anode and which is the cathode. Remember, oxidation occurs at the anode. They both start with a vowel. Or you can think of red cats. Reduction occurs at the cathode. So here's a summary of the different electrochemical cell types. For all of them, oxidation occurs at the anode, reduction occurs at the cathode. You got to get that straight. It's challenging, but you got to get it straight. In a voltaic cell, the anode is the source of the electrons. The anode is going to have the negative charge. The electrons are going to be repelled from that negative electrode, and they're going to flow towards the positive cathode. The cathode draws the electrons, the cathode has a positive charge. In an electrolytic cell, things are opposite. Electrons are drawn away from the anode, but now the anode has a positive charge. We're forcing them away. And we're forcing the electrons into the cathode, which is connected to the negative terminal. Yes?
Well, it's not really opposite. It's more because like electrons leave the anode, electrons leave the anode, electrons go to the cathode.
The charges are opposite.
Yeah.
The charges are opposite, but yes, the electrons are always leaving the anode and going to the cathode, but the charges are opposite because you're having to force it. They don't naturally want to go to a negative electrode. And the reason that the electrons are going in the same direction is because oxidation occurs at the anode and reduction occurs at the cathode. Any questions? Well, how do we predict what the products of the electrolysis reaction is going to be? We're going to start with the easier ones and move towards the more difficult ones. If we are using pure molten salts, then it's fairly easy to predict what's going to happen. The anion will get oxidized, the cation will be reduced. So in this example, we have sodium chloride. So we have melted sodium chloride in here. Chloride can't be further reduced. -1 is its lowest oxidation state. So it's going to be oxidized. Sodium plus can't be further oxidized, so this has to be the one that gets reduced. And so you form the elements, sodium and chlorine. There's a typo in that, isn't there? Look at that. Cl2 doesn't have a negative charge. That's not there. Any questions? I have questions for the publisher. What if we have mixtures of cations or mixtures of anions? Still a molten salt. Let's look at the situation where the molten salt has more than one cation. We have to consider which cation will be more easily reduced. So it's important to note that the standard electrode potentials in table 18.1 do not apply to molten salts. So you can't use those numbers to do anything because those are for everything in their standard states, right? So solids and liquids are in their natural state, and gases would be a pressure of 1 atmosphere, and anything in solution would be 1 molar. So we can't use the numbers, but the relative ordering is the same. So we can still use this to predict what's going to happen. So in this example, we're going to look at what if we had sodium chloride and potassium chloride mixed together and we melted it and we're going to run some electric current through it. What we're going to do is we're going to look at the two reduction reactions here. Sodium being reduced has a standard potential of minus 2.71 volts. Potassium, standard potential minus 2.92 volts. Okay? So the sodium is easier to reduce. Neither of these is wanting to go. It's not going to be a spontaneous reaction. We're not expecting that. It's an electrolytic cell. We're going to have to drive it. But this one at minus 2.71 requires less force, if you want to think about it that way. So the less negative electrode potential is going to be easier to reduce. Or you can think of in that list, the list is from positive to negative in order, right? Things at the top happen more easily. Reduction reactions at the top happen more easily, and as you go down, it becomes more and more difficult to reduce. So you just look at the two things, the two cations in the table. Whichever one's above is the one that's easier to reduce, and that's the one that will be reduced at the cathode. Does that make sense? I puzzled over this for a while in the garden this morning, trying to make sure that I had it really straight in my head so I could explain it to you. So if there's more than one anion, we have to figure out which anion is more easily oxidized. So sodium bromide, sodium chloride. We know that the sodium ion is going to be reduced at the cathode, but what's going to be oxidized at the anode? Is it going to be the bromide or the chloride? And this is where the way I'm presenting this differs a little bit from the book. Okay, so just keep that in mind. We have an oxidation reaction at the anode, right? So I've written these as oxidations. And when I write this as an oxidation, I change the sign on E0. Now, I was looking at a different book, and I actually kind of like what they did. What they did is they said negative E standard, just to point out that we flipped it around. But I'm not going to confuse things. I'll just maybe do it different next time. So this has a potential of minus 1.36 written as an oxidation. Bromide has a potential of minus 1.09 written as an oxidation. Which of these is less negative? The bromine. Bromide requires less voltage to be oxidized. It's more easily oxidized. So here in brackets I put my way for the oxidations. Reverse the equation, change the sign. That's what we've done with everything else, right, with delta H's and delta G's. And if you're looking at a list, think of this, if this was in the list only has reduction reactions, right? But we can visualize what would happen if we included all the oxidation reactions, right? It'd be twice as big, be really kind of complicated and cumbersome, but we'd still go from positive at the top to negative at the bottom. So look at these two and think, well, which one's going to be higher in the list? The one that's less negative, right? So the bromide is easier to oxidize. Any questions? If you like the book way, go ahead. That's fine. Just didn't make a lot of sense to me. Like too much stuff to remember. Okay, so we talked about molten salts and mixtures of molten salts. Let's look at aqueous solutions. When we do electrolysis in aqueous solutions, it gets more complicated. And unfortunately, electrolysis in aqueous solutions is usually what happens. So one of the complicating factors here is that you can get electrolysis of the water itself. Right? We just talked about that and looked at a picture of it. So the oxidation of water gives oxygen and 4 hydrogen ions and 2 electrons. The standard potential is minus 1.23 volts. But in pure water, is the hydrogen ion concentration 1 molar? No, it isn't. So is the potential for this half reaction in pure water really minus 1.23 volts? No, it isn't. We could calculate it, and I'll just write that up. I'm not going to do all the math, but E equals E0, which is minus 1.23, minus 0.0592 over N, which is 2, times the log of Q. Right? So you can calculate that. That is, oh shoot. No, that's okay. You just have to be really careful with your signs there and your Q's and make sure that you're doing Q and your standard potential here for the same reaction. But we'll come up with minus 0.82 volts for that. So it is a pretty significant change. So that's the potential for this in water. The reduction of water gives hydrogen gas and 4 hydroxide ions. The hydroxide ion concentration in pure water is not 1 molar. So we can do a similar calculation, and we find that this has a potential of minus 0.41 volts. Water is not standard conditions. So when we're looking at electrolysis in water, we have to use these potentials for the oxidation and reduction of water. And like I mentioned earlier, pure water doesn't conduct, but if we have an electrolyte in there, electrolysis can occur, and if the voltage is high enough, it will. Well, let's look at electrolysis of a sodium iodide solution. So oxidation occurs at the anode. So looking at oxidation reactions, we have 2 possibilities now. We have the iodide being oxidized, or we have water itself being oxidized. So just like when we had a mixture of cations or a mixture of anions, we need to look at their half reaction potentials and see which is less negative or which is more positive. So between these two, water and iodide, which one is actually going to be oxidized? The iodide. So that's the reaction that will occur at the the anode. For the reduction reaction, we also have 2 possibilities: the reduction of water, the reduction of sodium ion. Well, sodium ion has a standard potential of minus 2.71. The reduction of water is minus 0.41. So that's going to be easier to do. And so that is the reaction that will occur. So you look for each of the electrodes, the half reaction that occurs the easiest has the less negative or the more positive E is the one that will actually occur. You notice this is a very large negative potential. Those metals way down at the bottom, of that list of reduction potentials are called the active metals. And they react with almost anything. And so you cannot actually reduce any of the active metal ions using electrolysis in aqueous solution because the water is oxidized first. I'm sorry, reduced first. And so it's just not going to happen. Any questions? So here's an example of what's going on here. We've got an inert electrode. We've got iodide in here. The iodide will be oxidized. Over here we have sodium ion and iodide ion. We might want the sodium to be reduced, but it's not going to happen. The water is actually going to be reduced instead. And just to make things a little more complicated, there's something called overvoltage or overpotential. And this is an additional voltage that must be applied to get some non-spontaneous reactions to occur. So we just looked at this half reaction, the oxidation of water, right? And we did a calculation accounting for the lower concentration of hydrogen ions, and we found that the potential was minus 0.82 volts. Well, it turns out that that's not enough voltage to cause this reaction to go. It actually requires about 1.4 volts of energy to be applied. And the reason for this is kinetic factors beyond the scope of this discussion.
Lovely.
Isn't that lovely? Basically, they're saying, we're going to tell you that this exists, but we're not going to go into it. We're not going to explain why. It's complicated, okay? It's complicated. Lovely, yes. Okay, so let's do a problem. Predict the half reactions occurring at the anode and the cathode for the electrolysis of aqueous sodium sulfate. Oh, this is a fun one. Oh, those were not the, I thought I did this one, and I thought I brought the notes with me, but I did not, because that would be too convenient. So we need to look at our table of reduction potentials. Oh, look, it opened right there. So how do we go about doing this? Well, we've got two reactions, right? We're going to have oxidation and we're going to have reduction. It doesn't matter which one you put on top. So we've got two ions here. We've got sodium ion, we've got sulfate ion. Something's going to get oxidized, something's going to be reduced, but this is aqueous, and so water could be one of the things being oxidized or reduced, right? So let's write those half reactions in first, and we have to use the adjusted potentials, not the standard potentials. So the oxidation reaction for water, I'm going to leave out all the state symbols, is this one right here. And E, as written, is minus 0.82 volts. And if water gets reduced, we've got the other half reaction. Gives us hydrogen gas and hydroxide. And then, bless you, E is minus 0.41 volts. So those could both happen, yes?
So if we had something like this on a test where the water is a factor, do we have are those values given, or do we have to know how to find those values?
I would definitely give you standard electrode potentials, like the ones in table 18.1. Maybe not the whole table, but anything you might need. I would probably give you these as well, because I would prefer to test you on, can you calculate that in a separate problem?
Okay.
So I'll probably give you those numbers, but you could calculate them.
Yeah. Okay.
So what's the other potential reduction reaction? Potential reduction. Possible, we should say possible. What could be reduced here? Sodium or sulfate? Sodium could be reduced, right? Sodium plus 1 electron gives sodium metal. We looked that up, and that's minus 2.71. That's not going to happen. So between these two guys, water wins. So at the cathode, this is the reaction that's going to occur. Now, at the anode, can sulfate do anything?
Yes.
Well, can you find a reaction a half reaction in table 18.1 for the oxidation of sulfate? It is kind of a trick question. It's not in there. You can oxidize it. It oxidizes to thiosulfate. But since they're asking us this in the textbook and they don't give it to us, I don't think they intend for us to use it. There's one involving
Sulfate?
there's like sulfate being involved in the reduction of lead to oxide. We also find the reduction of sulfate, but not the oxidation of sulfate in this table. So we can't just flip this around because the sulfate has to be the reactant. So we got nothing up there. So this is the reaction that occurs at the anode. But since there's a reduction reaction for sulfate, maybe we should revisit what's happening at the anode. So sulfate plus 4 hydrogen ions plus 2 electrons goes to sulfurous acid and water. Some of these are standards and some of them are not. That E standard is plus 0.20 volts. So then we need to rethink these two, right? Question?
The values we have, the oxidation reduction of water, are what you would find here because we had to change them.
Because this is an aqueous solution, and so the hydrogen ions concentration is 10 to the minus 7, and the hydroxide is 10 to the minus 7.
And that one won't be the same either, though.
Right, this has hydrogen ion in it.
Yeah.
So we can't use the standard potential, we have to adjust it. Oh, man. Because when I was doing it this morning in my garden, it was lovely out there, by the way. It's a mess, but the air was lovely. I looked at this and I said, well, this is less negative than either of those. This is the reaction that should occur. Then I look at the answer in the back and it says, no, it's this one. I'm like, huh? They hadn't done any examples like that really before. I'm like, what? It's the hydrogen ion. Hydrogen ion changes everything. So Q for that reaction is the H2SO3 over the sulfate ion concentration and the hydronium ion concentration raised to the 4th power. Now what we're going to do is we're going to leave these in their standard 1 molar state. We don't really have any information about them. We have no reason to think that they couldn't be 1 molar, so we're just going to leave them that way. But we know that the hydrogen ion concentration is 10 to the minus 7. So then Q equals 1 over 10 to the minus 7 to the 4th power. So the adjusted potential equals the standard potential minus 0.0592 over, how many electrons in this one? 2 over n times the base 10 log of 1 over 10 to the 7th to the 4th power. Isn't that a lovely mess? You could do some mental simplifying for that. Could be dangerous. Or you can just plug it all into your calculator, which is what I'm going to do if I can stop messing up here. 592 divided by 2 times the base 10 log of So in water, this is minus 0.63 volts, not plus 0.2. This is E. This is E under non-standard conditions. So now we compare this minus 0.63 to the minus 0.41, and the minus 0.41 wins. Question?
Were you just decided to say H2SO3 and SO4 was 1? Like that a standard thing? You're just like,
Well, I think in the absence of any other information, you leave them alone. If it gave you the concentration, then you could actually figure out what the Q for that specific situation is. What we're doing here is, we're just kind of predicting what might happen under very limited circumstances. If you actually made this electrolytic cell and wanted to know how much voltage you needed to pass and what exactly the products were going to be, you'd need a lot more information. So we're just kind of giving you a little introduction to electrochemistry and let you know some of the things that are involved. Because there's also overpotentials involved here as well. Lovely, yes. Which is why you can spend years and years studying electrochemistry without running out of things to learn. Any questions? Now this is what I would consider a challenging problem, because you have to consider all of this business. And that's because of the 4H+. If you had one that had OH- in it, and this is an aqueous solution, you're also going to have to consider that. Now, if this was in 1 molar HCl, then the hydrogen ion concentration would be 1, right? And so then the standard potential would work. But it just says aqueous, so you assume it's in water. Just water with no other acid or anything. Okay? Stoichiometry of electrolysis. So in this electrolytic cell, electrons are essentially acting as a reactant. And as such, they have a stoichiometric relationship with the other reactants and with the products. So if we look at the copper plating here, the copper is oxidized to copper ion, and that involves 2 electrons. Those 2 electrons for every 1 copper atom run through the wire and come over here, and then 2 electrons, I don't know what's going on here. 2 electrons are available down here to reduce the copper ion and plate it onto, it looks like a spoon. Not sure why you'd want a copper-plated spoon, but whatever. Because you can. There's a lot of things that people do just because they can. So if it's 2 electrons for every atom, then it's 2 moles of electrons for every 1 mole of copper, and that's stoichiometry. Well, in stoichiometry, we often measure things in mass, right? We weigh stuff out on the balance, and we can figure out the product that we're supposed to get and the amount of the theoretical yield and all that kind of good stuff. You can't weigh electrons, but you can measure the charge. So we measure electron quantity in charge instead of mass. The number of moles of electrons we get from the total charge that has flowed through the cell. And that is dependent on the magnitude of the current and how long it ran. So Faraday's constant is important here because that relates Coulomb's charge to moles of electrons. And the definition of an ampere. 1 amp, which is what we use to measure electric current, is 1 Coulomb per second. So if you take the current, which is in coulombs per second, and you multiply by the seconds, you get the number of coulombs, which you can convert into moles of electrons. So, for practice, silver can be plated out of a solution containing silver ion according to the half reaction given there. How much time in minutes would it take to plate 12 grams of silver using a current of 30 amps?
3 amps.
Sorry, 3 amps. Yes, there's a decimal point. I was testing you. Good call. Well, what is 3 amps? 3 coulombs per second, right? And then we have Faraday's constant, 96,485 coulombs per mole of electrons. Now, like I tell my very beginning chemistry students, sometimes you look at a problem like this and you're not sure where you're supposed to start. And you look at this and you think, well, I think this is basically just dimensional analysis, but what number do I start with, right? So 3 amps, this is actually a compound unit, coulombs per second. That's probably going to be a conversion factor. Faraday's constant, coulombs per mole. That's relating 2 units. That's a conversion factor. 12 grams isn't relating anything to anything. That's the number we're going to start with. So 12 grams of silver. Well, we're going to use our chemical equation here and see that we need 1 mole of electrons for every mole of silver, right? But we don't have this in moles yet. We need to get moles of silver. Well, what's the relationship between moles and grams of silver? Periodic table behind me. 107.87 grams of silver per mole. So those units cancel out. Finding it. So now I've got moles of silver. There's 1 mole of electrons for every 1 mole of silver that gets plated. Stoichiometry, 1 to 1, right? Those units cancel out. So we've got moles of electrons. We need to get to time. Well, we're going to use Faraday's constant. 96,485 coulombs per mole of electron. Those guys. Now we've got coulombs, and we want seconds. Well, actually, we want minutes, but seconds is the next step. 3 coulombs per second, 3 coulombs per second, 1 second per 3 coulombs. And then to get into minutes, we need 60 seconds is 1 minute. I did all of that. I wonder if I still have the number in here.
6.
It's 59.6? 59 point something. 59.6. So 59.6 minutes, how many significant figures?
Oh.
2. So 60 decimal point minutes, or better, is 6.0 times 10 to the 1 minutes.
Yeah.
It's better. You don't have to like it, but it is better. Any questions? So you can imagine there's a whole bunch of questions we could ask using stuff like that.